Okay, class, so let's begin lesson number 58. By the end of this lesson, you should be able to use oxidation numbers to determine if a substance is reduced or oxidized. Use oxidation numbers to determine if electrons are lost or gained by a substance. Write half reactions to describe oxidation and reduction, and use those half reactions to balance redox reactions. All of the examples plus the steps for balancing half reactions are given in your guided notes. So I highly recommend that you print them out and follow along on Google Classroom, or you are more than welcome to take notes on your own, but make sure you take good notes. And no matter how you're taking the notes, make sure you have a Regents Chemistry reference table along so you can look up oxidation numbers. Let's get started. So what's a half reaction? A half reaction is a reaction that shows just an oxidation or just a reduction that occurs during a redox reaction. So here you can see we have two half reactions for this overall redox reaction. In our reduction half reaction, we can see that sodium's charge is going down from +1 to 0, and it is gaining an electron as we see the electron on the reactant side. And for the oxidation half reaction, we can see that lithium's charge increases. It changes from 0 to +1, and it loses electrons. Electrons that are lost are always written on the product side. So notice that in a half reaction, the element symbols are the same, and they include the charges, and electrons are also included. Every redox reaction must have an oxidation half reaction and a reduction half reaction. And these two processes must occur together because the number of electrons lost in oxidation must equal the number of electrons gained in a reduction. Recall that during all chemical processes, matter or mass, charge, as in electrons, and energy are always conserved. So here are the steps for writing and balancing half reactions. These are provided in the guided notes, or you can take a minute to pause the video and write them down if you need to. Let's look at this example together before we try 3 examples on our own. So here, what we have is we have a redox reaction. In order to determine if a reaction is redox, the first thing you need to do is assign the oxidation number of all the species in the reaction. So when we begin here with this reactant, it is a compound, and we know the sum of the oxidation numbers must add up to 0. So that information allows me to determine the oxidation number of the sodium and the chlorine. Now, the magnesium on the reactant side is alone, and it has no charge. So it must be an atom, which has no charge. And we can use these same principles for the products. From there, to write the half reactions, what you'll do is you'll find the symbols who are changing oxidation state. So we can see that sodium changes from a +1 on the reactants to a 0 on the products, and magnesium is changing from 0 to +2. Now, this is the first step of each half reaction. Notice the half reactions, the symbols are the same on both sides, but we must include their charge to show they are changing. Now we need to make sure charge is conserved. And right now, +1 does not equal 0. So you always are going to add the electrons to the more positive side to balance the charge. So here I'm going to have to add 1 electron to the reactant side. So sodium's changing from 1 to 0. That's a reduction in charge. Reduction is a gain of electrons, so the electron is a reactant. Now here we need to balance the charge. This is the more positive side. So we're going to actually have to add in 2 electrons here to balance the charge. So 0 does equal +2 plus 2 negatives. Now the last problem we have is that sodium gains 1 electron, but magnesium is losing 2. So we need to make sure that the electrons gained are equal to the electrons lost. So we need to find an integer to multiply by so we can arrive at the LCM between 1 and 2. So we're going to multiply our sodium half reaction by 2. That means I will have 2 electrons, 2 sodium ions, and 2 sodium atoms. And in this entire process, that's important because that means that 2 electrons gained come from the 2 electrons lost. So let's do this problem together. Make sure you have your Regents chemistry reference table out so you can look up oxidation numbers. See if we can tackle this problem together. So the first step is to assign the oxidation numbers. So copper here is alone. So copper could have an oxidation number of +1 or +2 in a compound, but alone it is a neutral atom with 0. Now here is silver. Silver has the oxidation number of +1 in a compound. And here we have nitrogen and oxygen, part of nitrate. This is a polyatomic ion on reference table E, and this whole ion has a charge of -1. Now when I look on the other side, I see the nitrate again, and this whole ion again has a charge of -1. So copper could be +1 or +2, but since this entire nitrate has a charge of -1, but I have 2 of them, copper must be +2, and then silver is 0. So once we do that, we have to find out what's oxidized. So copper is changing from 0 to +2. That's not a reduction, so that must be the oxidation. So I'm going to write copper, which is 0 on the reactant side, and copper, which is an ion with a +2 on the product side. Now, after we write in the element and the charges, we're going to have to add electrons to balance the charge. We always add electrons to the more positive side. So I'm going to add 2 electrons to the product side. So remember that oxidation is the loss of electrons. For the reduction, we can see that silver is changing from +1 to silver with a 0 charge. Now again, I need to add in the electrons to the more positive side, but this time I only need 1 electron. Now that's a problem. I cannot lose 2 electrons and gain 1. I need to make them the same. So the multiple between 1 and 2 is 2. So I'm going to multiply everything here by 2. So when I have my balanced reaction, on my reactant side, I have copper with a charge of 0, and I have silver with a charge of +1. But since I had to multiply the whole reaction by 2, I actually have 2 silvers. And then on the other side, I'm going to have copper with the charge of +2, and I have silver with a charge of 0, but again, I have 2 silvers. Here's another practice question. Notice that in this equation, the spectator ions have been removed. That means all of these species will undergo a change in oxidation number. So we have to find the oxidation number of all the pieces. Notice that the iron on the reactant side, they give us the oxidation number as they do the magnesium on the product side. So we don't have to do any work for those. And then here, magnesium is alone in its natural solid state. So this has an oxidation number of 0, as does the iron over here. So what we can see is the magnesium oxidation number changes from 0 to +2. 0 to +2 is not a reduction, so that's an oxidation. So to write the half reaction, I'm going to write the symbol on each side of the arrow. Then I'm going to include the oxidation number. The last thing I need to do is to write in the electrons. We always put the electrons on the more positive side to balance the charge. So magnesium will lose 2 electrons. Now here's iron. So to write its half reaction, I'm going to write iron symbol separated by the arrow. And then I'll put in the charges. So this is 3 plus and this is 0. So for this, I'm going to have to put in the electrons on the more positive side. To balance the charge, I need 3 electrons. Now we have an interesting dilemma. Our dilemma is that the magnesium is going to lose 2 electrons, but iron needs to gain 3. So I need to determine what the LCM between 2 and 3 is. The LCM between 2 and 3 is 6. So I'm going to have to multiply my magnesium by 3. That will turn this into 6 electrons. So every magnesium in my reaction, I'm going to multiply by 3. And my iron, I'm going to have to multiply by 2. So every iron in the reaction, I'm going to multiply by 2. So in order to find the balanced reaction, what we do is, since there are the same number of electrons on each side, the electrons will cancel out. And then we just add up these two systems. Again, it'll look just like what's above, where I have 3 magnesiums and 2 iron ions, yields 3 magnesium ions and 2 iron atoms. And the last step you want to do is just to check that this is actually balanced by making sure charge is conserved on both sides. So this is 0 plus 2 times, this is 6. So this entire charge is plus 6, and then this is plus 6 and 0. So this entire charge is plus 6. So we're indeed balanced. Let's do one more together. So here we have aluminum, and it has no number and no partner. So its oxidation state is 0. And again, this zinc is provided and this aluminum is provided, but this zinc must be 0. So we have to find what's oxidized. So oxidation means a gain in oxidation number. So aluminum's going from 0 to 3. So to write its half reaction, we're going to write the symbols separated by an arrow. And then we're going to write in the charges. And the last thing we need to do is to write in the electrons. Electrons go on the more positive side to balance the charge. And the zinc, we're going to write its symbol separated by the arrow, include the charges, and then we're going to have to put in electrons on the more positive side to balance the charge. So here, again, we are losing 3 electrons, but zinc will only gain 2 electrons. So we need to find the LCM between 3 and 2. That means every aluminum is going to be multiplied by 2 to make 6 electrons. I'm just going to put the 2 up here for the coefficients in the balanced reaction. Zinc, we need 6 electrons, so 3 times 2 is 6. And so every zinc is going to be multiplied by 3.
Let's see if you can write the half reactions and balance this reaction. Take a minute to pause the video and try this on your own.
Did you balance it like this? Remember that the coefficient of 1 that is in front of each zinc does not have to be written, but your answer is not wrong if you did write the coefficient of 1 in front of each zinc.
This concludes lesson number 48. Make sure you've taken good notes. You bring your questions to class, and I'll see you soon.